So your titrations will be based on your 3 trials, and then you average them. So essentially, you're trying to find the concentration of acetic acid, and then you do that based on your endpoints 3 times. You take your 3 different concentrations, and then you average all 3 of them. So I'm going to just write up some of the numbers that we're going to make some assumptions on. The first was not an assumption, but the actual concentration of sodium hydroxide that I gave you, which was 0.471 molar NaOH. And then I'm going to assume that the concentration of the acetic acid was roughly like let's say 900 molar, roughly. So you guys are going to have different numbers here, right? You're going to have whatever your exact concentration was of your acetic acid. Following? All right, so before we start, I'm just going to take a look with you at analysis question number 6. That's really what I want to focus on. If you have other questions prior to that, you can ask me separately. So looking at number 6, it says, first part, your Ka, let me just write this down, is 1.8 times 10 to the negative 5th. So initially, calculate the pH of vinegar. So that means what was in your Erlenmeyer prior to any addition of anything? What's the pH of vinegar? Without a pH meter, we don't know, right? We can't take that, except that we can calculate the pH based on this Ka value, what our assumptions are of this dissociating. So initially, there is no base reaction in here. All we have is acetic acid in water, dissociating weak equilibrium, going to the conjugate base plus H3O+. Agreed? So if we have that already floating in our beaker, we're going to use our Ka value, and we're going to calculate our products, which is going to be the conjugate base and hydronium, all over the concentration of acetic acid, which we find from our equivalence point. So we will find our pH once we find out what H3O+ is. Is everybody following this? It's literally like what we've done since day 1, even with equilibrium at all. How do you find the H+ concentration? You just do products over reactants. There's no actual reaction in there. It's just the dissociation. All right, so we have this piece. We need this piece. So we need to go back and find our initial concentration, which is what you guys should do when you do your 3 trials. You find your endpoint, yes? And your endpoint, say it was, I think most of you were around 18 milliliters, something like that. You find your moles of OH minus, which then will equal your moles of your CH3COOH, and then you divide that by your exact 10 milliliters that you used, and then that will give you roughly your concentration, which is what I'm making the assumption today, that it's going to be somewhere around 0.9, okay? So you're going to do that 3 times. I'm assuming you already did. So that would be the concentration here that we're going to plug in. Everybody following that? You get this answer from your endpoint. So now I'm going to take my Ka value, 1.8 times 10 to the negative 5th, and that's going to be equal to, and we're calling this x squared because they dissociate into the same amounts, right? This goes away by x, this goes up by x, so this is 0.900 minus x, and then I'm going to cross that out because this is greater or less than 10 to the negative 4th, and I'm going to solve for my x squared value. So what range should my pH be in? Knowing that this is a weak acid, what should my pH be roughly? Somewhere greater than what? Definitely greater than 1, probably greater than 2. Well, we'll see what it is. So let's calculate this. 1.8 times 10 to the negative 5th times 0.9, square root that, and we get H+ concentration, which is our x value, is 0.0040 molar. So I take the negative log of that, and my pH is 2.340. 2.40. That should make sense, right? It's acetic acid sitting in that beaker, so the pH should be 2.40. Nothing has happened yet. Any questions? Do you have this sheet out while you're doing it? Okay, so before any titrant is added, you use Ka, which is products over reactants. You solve for x squared, find H+, then use pH to the negative log. right? Now, vice versa, if I give you the pH, what would you do? If I ask you to solve for Ka, what would you do? If I say at the end point, blah, 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 the pH is 2.40, you tend to the negative 2.40, and then you plug both of those values in here using your initial concentration here, and then you solve for your Ka. Just look at what pieces of information are given to you. But before any titrant is added, you're always using this Ka expression. Okay, the next thing says at first sight. So that's what we're going to look at when we say part B says what was the pH of the solution after 4 mils of titrant were added. So now that we have our titrant going in, we have a weak acid-base reaction. Everybody has this? So at this point, we're going to create a buffer. So this is at 4 milliliters. So now you have your acetic acid floating in there, plus hydroxide, one-way arrow. You're going to make the conjugate base, and you're going to make water. So our initial concentration here is 0.900 molar, but how many moles are of that in the water? So you have to go back and calculate that you're going to use your 0.01 liters, and you have 0.00900 moles of this in there. So if we put 4 milliliters in of our sodium hydroxide, now I'm going to take the molarity of the sodium hydroxide and calculate how many moles of that goes in. So this is going in 0.00188 moles. So what's your limiting? Limiting is the one that's less. OH, right? We haven't reached our equivalence point yet. So I subtract that out. Subtract that out. This is now 0. We subtract out. And then I add, this was 0, there's none of that in there, right? It's negligible, whatever amount was in there. And then I'm going to add the 0.00188 here. And now you can recognize that you have, in this solution, you do have a buffer. Or you can use your Ka expression. Remember I said there's 2 ways to go about it. So if you take your original Ka expression, now you have this, and then you would have your Ka, and you would just solve for essentially H3O+, because that's your original Ka expression, not with the base. Or you use Henderson-Hasselbalch. So now if we use Henderson-Hasselbalch, we're going to do pH is equal to the negative log of that Ka, which is 4.74, plus the log, and then you're going to do the concentration of, from the acid reaction, this base, which I can just eliminate my volume because it's going to cancel out, over the concentration of the acetic acid. So, plus the log of this. So my pH here, I just plugged it all in. I didn't round for sig figs at that point, but 4.17. All right, does that make sense? Why? I'm talking about the pH. Why does that make sense? We added base, right? We're not at equivalence point. When we get to the equivalence point, where will the pH be? This is a weak acid with a strong base. Did you say 6, 7, 8? It's going to be basic, right? What's pH at strong acid, strong base? 7. So if you're with a weak acid and a strong base, the base is going to overcome that part of it. We can talk about that at equivalence. You'll see exactly what happens. But you essentially have base floating around even at the equivalence point. So your pH is definitely going to be above 7. We're not at equivalence point yet. We're just increasing the pH as we go. All right, so we can do this over and over and over and over again until we reach our equivalence point in which these moles will be equal to these moles, right? So say I just said now 8 milliliters, 9 milliliters. You just would keep repeating this process until you gradually find the equivalence point. Yes?
So acetic acid, the moles that you use on the red shirt would stay the same?
Yes. You're going to just start over each time. So then what was the pH at the equivalence point? All right, so we need to assume we used 18 milliliters. You guys are going to calculate your endpoint as an average of your 3. So you'll take all of your volumes, and you're going to calculate that as an average so you can figure out how many moles of OH went in, which is the same thing as doing, essentially, you can take your original moles there, but just make sure you're using your average, okay? So at that point, at equivalence, I'm just going to erase this portion. So at equivalence, our moles of acid are equal to our moles of base. Everybody agree? So if these are my initial moles of acid, then I'm essentially putting in the exact same number of moles of base. This will be different for all of you. When you subtract those all out, we end up with 0 moles on both sides. But then we end up with 0.009 moles of our conjugate base. All right, so you can't use the Henderson-Hasselbalch at this point, and you can't use a Ka expression at this point for the acid, right? There is no acid sitting in there. So look at your sheet. What does it say happens at equivalence? All the HA has reacted and made A minus. Do you see that? That's the conjugate base. So find POH using KB of that. Essentially, this is like me saying to you, I have base sitting in water. What happens to it? So what I'm really doing is I'm taking this as my reaction, and now I'm going to write my KB expression from this. See why it's basic at equivalence point? Because you have base floating around. So now I'm going to do a KB expression is equal to the acetic acid times the OH concentration all over the acetate ion, which now I know what moles are in there, and I can calculate the concentration of that. So we're going to find KB from doing a KW. So KW is equal to Ka times KB. So let's solve for that first. So 1 times 10 to the negative 14th. Oops. Divided by our Ka, 1 times 1.8 times 10 to the negative 5th. And remember that Ka and Kb are for the conjugate base pairs, right? Conjugate acid base pairs. So my Kb expression here is 5.56 times 10 to the negative 10th is equal to, and now I'm going to write x squared over, and I'm going to find my concentration of this. So at equivalence, I take these moles and I divide them by the total volume. So your total volume was your 10 milliliters that you put in, plus your equivalence volume. But in our case, we need to use the average equivalence volume, which I believe we're assuming it's 0.018. So that was 18 milliliters here. So you put in 28 milliliters, so 0.02800 liters, and we'll solve for the concentration of the conjugate base that's floating around in there. So this is all over 0.3, just trying to make sure I keep track of sig figs a little bit, 321, and then we'll solve. So now you're solving for POH. And so this means X, or my OH concentration, is 1.34 times 10 to the negative 5th. So I'm going to negative log that to find my POH. So POH is equal to 4.87. I'm using a lot of sig figs here. I should just keep track, but I didn't. And then I'm going to subtract that from 14. And my pH at equivalence is 9.127. Does that make sense? So the pH should be slightly basic at the equivalence point because you literally have a base sitting in water. When you have acid, strong acid, and strong base, your pH is 7 because there's nothing floating around except for water. And then just recognize is if I reverse this and instead I had titrated a base with a strong acid, right? I can reverse these. Then at equivalence, I would have acid being dissociated into base, right? These, you have to remember that these can be reversed. I don't have to have a base being the titrant all the time. I can have an acid being the titrant. Yep.
I forget, which volume did you say you divided the moles by?
Total, always total floating in there. Because it's what's currently, what is this concentration currently at equivalence point? That's what we're plugging in. Are you following this? Okay, last part is that it asked what would be the pH essentially when we've gone too far. So we found the pH at the equivalence point. Now what is the pH after you added 35 milliliters of titrant? So I'm just going to erase this part here. So now you've put too much in. So what should your pH be? It should be that of a strong base floating around. So now I'm going to calculate if I put in 35 milliliters like it asked, and I'll solve for how many moles of base are floating in there now. So now I have 0.0165 moles of base. So now obviously my limiting has switched. So now I subtract out how many moles of the acid would be reacting with the base, and then I'm going to make that on the other side. So this ends up being 0.0165 minus 0.009 is 0.0075. 4 moles of that are remaining. And then even though you are making moles of this on the other side, because this was 0 initially, and you're adding 0.00900 of this is going to be negligible, right? Because the base concentration itself is going to overtake any base reaction that we would have gotten over here, right? I'm just going to point out one more time that when we do we essentially have two reactions going on. We have OH just floating in there, but then we also have this happening where this does its own dissociation. But the amount of OH that would be present in here would be driven back to the left according to Le Chatelier's because you would have excess OH in there, right? So we don't really care about whatever happened on the dissociation or the ionization side over there. All right, so now this is the excess OH. So look at your sheet. What does it say to do? When you've added too much, it says use the ice chart to find the moles of excess OH. We just did that. Divide it by the total volume. So now we're going to add up our 35 mils that were in here plus the original 10. So we have 0.0450 liters. And then we're going to find pOH directly from the concentration of OH floating around. So this concentration of OH is 0.16.17. I'm going to take the negative log of that. This is pOH. At this point, pOH is equal to 0.77. So 14 minus 0.77 is 13.33. 23. Sorry. And that makes sense because it's the pH is of a very strong base. So if you follow this exactly, it should make sense to you. Really, the only tricky part is recognizing at equivalence point, you need to switch the reaction to recognize that it's a base at that point. And there are a variety of ways to solve this. This is just the technique that I've been teaching you to follow. But if you really grasp acids and bases, we've talked about this before, there's more than one way to solve this problem. You can use Kas throughout. If you understand what's happening to the reaction and you write out all the reactions, you should be able to figure out a way to solve it based on Ka, Kb, or Henderson-Hasselbalch equations. And then the rest of that was just asking you to draw a titration curve, so make sure that you plot it like we've discussed before. And then the rest of the questions were just sort of asking you preliminary stuff leading up to this whole part.